get started for the last session of the conference. Thanks for staying until the happy ending. The next speaker is Ben Aloha from the University of Cambridge, speaking on banks.
Thanks very much. So, is the microphone working? Yeah, you can hear it. Okay. So first of all, an apology. I'm really a physicist masquerading as a mathematician. So the language used in this talk and the way of thinking will be different to most of the other talks in this workshop. But I'm going to describe basically what amounts to nothing more than an particular implementation of the Metropolis algorithm that allows one to sample from highly isolated maxima. So what we want to do is sample. I'm a high energy physicist actually, so what we're interested in doing is fitting rather unconstrained data to unconstrained models with quite a few parameters to some fairly indirect data and making inferences, probabilistic inferences in a Bayesian sense on those. And so what we want to do is have some kind of sampling from some probability surface in n dimensions, and our problem is actually 8-dimensional, so it's high enough such that a straightforward scan isn't possible, but not ridiculously high. And we have this problem of well-isolated maxima. So the distance scale between the maxima of the surface we're trying to sample is much larger than the thickness of the spikes at each side. And not only that, each of these maxima actually have some degeneracies, and there is some roughness associated with them, so we can't calculate derivatives very accurately. And there's all sorts of and there are also hard discontinuities, where if you go in a certain direction in parameter space, all of a sudden you hit a physical boundary and the probability goes to 0 because the model no longer makes sense. So it's a really nasty thing to try and sample from and do inference on. But of course, Metropolis, plain old Metropolis, is kind of designed for things like this. Apart from the isolated maxima. So all we did was mess about with the Metropolis algorithm. In fact, just changing the proposal, picking a particular proposal distribution which uses a cache or a bank of clues in order to help you sample from the different maxima and normalize them with respect to each other. And it will work in general. So you can even have completely topologically separate spaces, and in fact you can still sample from the ensemble of the spaces, as I'll show you. And then we produced this work around May last year, and around the same time there was this other method in the astrophysics community that was proposed, multimodal nested sampling. They've got various implementations of them. One of them is using ellipsoids. And so I'll kind of, hopefully if I get time, I'll describe which one's best under which conditions between these two methods. Oh, I can do that, can't I? Yes. Okay, so you all know good old Metropolis. It's basically blind drunk sampling. So the idea is that Mr. Spock's been at the whiskey. He's on a planet surface and he's a bit cold, and he's completely blind drunk, and he's trying to find a place where it's warmer. So he's staggering about a bit, but he tends to go where it's a bit warmer, and of course that's Metropolis, basically. So okay. So so each step, say, you can view as a sampling from this space, and of course consecutive steps are not independent samples, they're correlated and so on. Okay, but a priori, of course, we don't know. We have to set some width for the step size that we're going to use of the consecutive step as from the. So x here marks the positions in n dimensions, and p is actually the heat that Mr. Spock feels. In terms of the high energy physics model, it's the posterior probability that it reproduces the data. Okay, that's fine. So, of course, you go through the whole Metropolis thing. If you run for long enough, then the final density of points is proportional to the probability, and you can use all the list of points as a sampling and do statistical inference on those. So, in particular, you can do parameter estimation and so on. I'm not used to using this thing. Okay, so the problem with blind drunk is when there's two hot bits on either side of a bridge, and in the middle it's very cold. And so, Mr. Spock, who has a step size of the distance between these 2 points here, doesn't tend to go very far, and in fact needs not to if he's going to be able to sample all of this hot region. But we want to find the existence of this other hot spot, or this other high probability space, and of course, it's very cold there, so he tends not to wander very far into the cold region.
So you don't assume that you know anything about the modes or their approximate location or anything like that? Or
well, you'll see that in fact what we're going to do is do some prior scouting investigations and get some information like that. That's right. But it turns out in our problem, I mean, a priori, you don't know where they are. It's we don't know conditional probabilities, so we can't use any of this Glauber dynamics that's very, at least in an obvious way, that's been very popular in this conference, for instance. Okay, so of course what you could do is you could tell Mr. Spock to take large strides, large enough so that he could kind of stride across the bridge. But then, of course, he'd be very, the efficiency is going to be low because on the whole he won't be able to sample very well from within one of these spikes of heat here. Okay. All right, and all bank sampling does is it says, well, you just do a prior run, or lots of prior runs with low statistics, and you find the existence of the modes, and you find out roughly where they are. So in this case, you might find either end of the bridge, and then what we want to do is just set the proposal distribution to reflect the positions of those modes. So it's nothing very fancy, it's all pretty trivial. Okay, so this is like having Mr. Spock on the bridge, but James T. Kirk's looking down, and every now and again he's going to throw the teleport button and teleport him to the other side of the bridge where it's also warm, so you can go and sample there. That's the basic idea. So it's a simple idea, works very well. Instead of so K is a kernel for, based on the current position X, it gives you the next proposed position xt, so it could be a Gaussian shape or some local distribution. And so usually in Metropolis, in most implementations, you just have this bit. But now we have all these banked points that we found somehow through earlier scouting expeditions or whatever, and their positions are denoted by y, and they come associated with the weight, which would be proportional to the temperature in this case. And we just say, okay, well, lambda's the probability that Captain Kirk presses the teleport button on any particular step. So Mr. Spock's allowed to wander around a fraction 1 minus lambda of the time, but on a lambda chance, he's going to teleport to one of the other hot places. Okay, and obviously you just have to take this into account in the usual Markov chain, Monte Carlo way, Metropolis way, in order to preserve detailed balance. Oops. Okay, so I'm going to show you a bit later, more or less, what our surface that we're trying to model, which is in 8 dimensions, looks like. But as I said, there are well-separated modes, but the modes themselves contain degeneracies within them. And so we have this toy model, which we call the two chimneys model, which looks like this. So this could be, the vertical axis could be the temperature, for example, and then these are coordinates on the surface of Mr. Spock's planet, or indeed it could just be a probability surface, and then there might be other, lots of other dimensions involved, which could be flat. Say that would model our surface quite well. So this is just these are just parameterized with this kind of circle Gaussian profile function, which is given here. So we just add together these two kind of chimney pots, and we want to see how well bank sampling does. So on your scouting expedition, you should do something like start off 100 runs, just burn them in. So just run long enough for them to find a reasonable local probability maximum point. You start from a random starting point, and then use those. And then when you compare how compatible the chains are, you'll find that they're not compatible at all. Some of them will be wandering around this kind of region, and the other ones will be wandering around there. So now you take some subset of them, if you take a few thousand, and it's semi-automatic, so you can do all the scouting and stuff automatically, but what you'd want to check by hand beforehand is that you've actually got, you're sampling the modes. So you've got some points, at least one point in this one and at least one point over here. And it's helpful if you've got some kind of similar number in each. Fine. So of course when you just do a simple Metropolis run, you just tend to sample around here, and then bank sampling goes around here and jumps back and forwards. So that here we show 10,000 samples with a certain width, common width between the two, and it's clear that it's kind of trivial really that bank sampling is going to be able to do it. All right, so one thing you might worry about is this probability of teleportation. And here, I think, if I remember rightly, we set it to be 0.1. And you might say, well, how finely tuned does that have to be in order for this thing to start to sample reasonably converge in a reasonable amount of time? And so we just check the dependence on this chance of teleportation. So here's a log plot. So what we did in this case was start all of the chimneys off at this x value of -2, and the average x value from all the samples should be +2. So anything that ends up down here hasn't actually sampled correctly between the two chimney pots. But you can see that so if you set this probability, at least for this problem, between per mil level up to around 1, order 1, then you get the correct answer, basically. The vertical bars are the uncertainty from the simulation that we give. Okay. All right, so you've got to be a bit careful up at the high end. Obviously, lambda is 1 is kind of the importance sampling limit, where you're really just using some parameterization of the previous scouting run in order to get samples. And as you get very close to that limit, the efficiency goes through the floor. It gets pretty bad. And the reason for that is, so here is an example with lambda of 0.99. So this says that 99% of the time, James T. Kirk presses the teleport button. And what happens is basically the Q factors that give you the detailed balance property tend to mean, in this case, that once you've got to a certain bank point, you're very unlikely to move away from it. And you can see one of those examples here. So for our problem, this toy problem, we ask what values of this parameter, this teleportation probability is safe, and there's some large range which will give you reasonable answers.
Something I don't understand. When you get teleported, you go to a random bank point.
Yeah.
Based
on the weight.
Yeah. So in the right-hand picture there, why it looks as though most of the time those sort of big black blobs are where you spend most of your time. I think.
Yeah. So I should have explained that.
Why did one get stuck so often in this?
Yeah, it's because of the Q factors. With such a high bank proposal,
Some of the weights dominate the others.
Yeah, it's this problem. It's this, in order to get detailed balance, the chance of jumping from some point to another point, basically the banked points themselves completely dominate all of the probability distribution. So if you stray off a little bit from the bank point, you've got to stay there for ages in order to, balance things up so that the chance of getting back is the same, basically. So that's what. If you put lambda too high, that's what kind of kills the efficiency in that case. It's not really clear. It just happened that those cases gave the right statistics here because the way we set it up. But if you look in detail, it doesn't work for too high lambda. Okay, so we have a particle physics context that we wanted to do. And this is just an example of a schedule that we found to work. So we did 10 ordinary Metropolis runs to start with 100,000 steps in each, and completely random starting points over some box of parameter space that we're interested in. And then from the above runs, we obtained 5,000 random samples, independent samples, and we just put those into the bank. If a few thousand is good. It depends on how many modes you've got. We only had a few, so this was absolutely plenty of modes. And then, of course, the weights are set proportional to the number of repetitions of the point in the bank sample. That's not the only thing you could choose. You could also choose the posterior probability given by the statistical analysis. And then after that, we did the proper runs using these banked samples, and it was 10 times 500,000 then. Okay, and this is what we got. So it's an 8-dimensional parameter space. So you're probably not so interested in what they are, but these are the different parameters. They're particle physics model parameters, and we did a fit to indirect data, as I said. And basically, the height of the surface is given at any point in this parameter, marginalized, or otherwise, in other words, integrated over the unseen parameters, is given by this color scale here. So, and there was a discrete parameter, which is the sign of this parameter mu. So the magnitude of mu is fixed, but the sign is not. And we get different results depending on which sign you choose. So just focus on mu positive for the moment. So that relates to this top figure. That one is the marginalization in 2 different dimensions, and this one in 2 different dimensions again. And you can see it's really pretty nasty. You've got sort of a large mode there, and then some degenerate spike coming out here. There's like a long tail here that's difficult to see. There are obviously 2 modes here. That's actually due to the dark matter properties of the model, and so on. So it's really quite a nasty thing that's difficult to just parameterize that analytically or something. And then even worse for this other sign of mu, the separation between the different modes is actually worse. And these surfaces are completely horrible. There's a numerical error associated with calculating the temperature or the height at any point, and that's of the per mil level. So even if we wanted to calculate derivatives by finite differences, we get huge errors in that, which is why Gibbs sampling and HMC is difficult to use. Okay, so what we could, but anyway, bank sampling worked very well. what we actually did was have some bank samples in here and some bank samples here. And so at the end of the day, you can look, and once you've done all of your bank sampled runs, you can normalize the probability, the integrated probability density in here with respect to that one, and find out how likely this parameter is to be, the sign of this parameter is +1 rather than -1. And so that's what I was saying about these completely topologically separate spaces. Okay. So the competitor that I mentioned to this is based on an idea by Skilling, who was here in 2004. And so, okay, Skilling wanted to calculate the evidence. That's the integrated probability, obviously, under this surface. So the notation is the parameters of these big thetas in d dimensions. The prior probability distribution is this pi, it's a function of the parameters in general, and the likelihood is also a function of parameters L. So that's the thing that the data gives you. And we define the prior volume as just above some certain likelihood lambda to be this x, which is the integral of the prior, in that region. And then the evidence is just the integral over the whole parameter space of the likelihood times the prior, which, as you can see, is just the integral of this likelihood as a function of this x from 0 to 1. Okay, so if you could sample from x given this constraint and then integrate it, you could calculate the evidence, which is kind of the hardest thing to do when you're playing this game. Parameter estimation is easier than calculating this evidence. So what Skilling said was, well, let's have m live points, and then we can calculate the likelihood for each of those points, and we'll come up with a way of estimating this prior volume between the live points. So we can imagine having the prior volume at 0 at the absolute global maximum, and it's 1 at over all of the space, and then our points are at various points in between 0 and 1, and we order them according to which is biggest. Okay, and then we're going to estimate z. Then, if we could have that sampling, then z is just this integral, and we can just estimate that with the trapezium rule, for instance. Quite easy, if you have that sampling. So we imagine the parameter space like this. We have iso contours of likelihood within it, and we want to work out, or estimate the volume within there. Okay, so what we do is we start off with some live points, and the one with the lowest likelihood, this L1, we try and sample from within that surface, proportional to the likelihood, and so then we replace this lowest likelihood point with, the new point that's sampled from within that surface, and then that's just like that will give you, on average, this new point will just be t times the prior volume within. So the prior volume contained within the new point will be a parameter t times the prior volume within the old point, where the probability distribution for this prior thing goes like this, basically. So what they did was approximate the iso likelihood contour by n live points sampled within a d-dimensional ellipsoid. So obviously that doesn't cover all of the surfaces you can think of in particular hours. But anyway, for simple Gaussian problems it would do. And it's you just determine the ellipsoid by the covariance matrix of the live points. So it's pretty simple thing to calculate. And of course, because it might not have a Gaussian shape, the thing that you're after, the mode that you're after, you enlarge it by some factor f. F is a free parameter. They chose 1.2 in order to, still get points that are more or less within what you want. That comes, the larger you make f, obviously, comes along with efficiency. You save less efficiency. Okay, and then they use a clustering algorithm to identify distinct, well-separated ellipsoids. So they use x-means, and so these ellipsoids find the isolated maxima. And if a proposed point is in several of these ellipsoids, in other words, if they're overlapping, there's a way of dealing with that, and you just accept the point with probability 1 over n, and that will solve the overlapping problem for you. Okay, and so when they applied their method to the two chimneys model I mentioned before in d dimensions here, with this ellipsoidal sampling, you find that it works very well, but it's got fairly nasty behavior at very large numbers of dimensions. And so instead of the ellipsoids, they start using Metropolis with 20 steps to do the sampling within the iso likelihood contour, and of course that scales better with number of dimensions, and the efficiencies here. So at high dimensions, this is what you would use. Okay. So their method also works. We've tested it on our particle physics likelihood, posterior surface, and it also, can be used to produce samples and, in fact, calculate the evidence, which we can't do with bank sampling. So, here on the summary, I've just compared the two different methods. So they both will allow to deal with isolated maxima, and actually they both allow determination of ratios of the evidence between isolated maxima. In fact, compared to this nested sampling, the bank sampling it can't just calculate one number, which is the evidence. It has to always rely on evidence ratios, and it can't calculate that ratio as accurately as the nested sampling. In fact, the nested sampling can get very accurate within a reasonable amount of time. It's easier. The bank sampling is easier to implement. It's just Metropolis, basically, with a certain proposal function, and it's able to efficiently deal with cases where the prior is numerically determined for each point. In other words, you don't know a priori how to sample from the prior, which you need to be able to do for nested sampling. So if you've got some flat prior, obviously you can do nested sampling on it. If it's some weird function, which was actually the case for one of our models, you can't efficiently do that in nested sampling. Okay, thanks.
Questions?
In general, if those modes are very well separated, and you have 1 point from each, life is better, isn't it, than if the modes start... if they all merge completely, then it's good, then it's just one mode. But if they are in between, wouldn't that seem to be the toughest, because your banks might get confused as to whether they are in the first mode or the second if they intersect a lot. Maybe the second.
Are you talking about nested sampling now, or
right?
Which bit are you talking about? Nested sampling, or
No, the bank sample.
Bank sampling. Okay. Well, it's kind of designed so. We have these two modes, like you say. Okay, is that what you? And then.
Maybe closer.
But if they're...
if they're a bit close, if you have something like this.
Yeah.
Oh, it's still okay, because you're going to get some bank points around there, and in fact, there's no real harm if you've only got one mode and you still decide to do it via bank sampling. What you lose is just a fraction lambda, because you don't win anything from teleporting particularly. So supposing all your bank points are in like a crap place to be, and you never use any of the bank points, then your efficiency goes down to 1 minus lambda, which is 90% typically. of what it was. So you don't really lose anything. Well, you can lose 10%. Yeah.
Do your bank points have to stay the same during the algorithm? I mean, it seems you invest some time in setting up a bank, and then you're running for a long time, and surely you're getting some much better samples later on. Can't you update your bank as you go?
That would be nice, but I think that would break detailed balance, and so you'd lose the Markov property, which you need, unless you did it in a very clever way.
For the second burn-in time.
Yeah. But I mean, that's kind of a second burn-in time is basically what we're doing. You can consider this thing as the first run as being a sort of, first burn-in, I guess. So, I don't know, you'd have to think pretty carefully about how you'd do that, and I think you'd want to switch that feature off, eventually. But it seems to work. I mean, it's trivial. There's nothing very amazing about it. But it just works really well, so it's kind of practically it's a nice tool to have.
Okay. No further questions. Let's thank